Hello everyone. I hope that you're all doing well today. In the last lecture, I showed you the binary Golay code C23, and we proved that this code is perfect. I also defined the extended binary Golay code C24, and we proved several properties about this code. We showed that C24 is self-dual. We also showed that C24 has a nice GM such that when you swap the two halves of the GM, you get a second GM for C24. And in fact, both these GMs are also parity check matrices for C24. We also proved that C24 has distance 8, and hence is a 3-error correcting code. In today's lecture, I'll show you a decoding algorithm for C24. The goals of the algorithm are simplicity, efficiency, and minimal storage. I'll remind you that C24 is a binary code of length 24, dimension 12, distance 8, and error correcting capability 3. We have a generator matrix G for C24 in standard form, where B is a 12 by 12 symmetric matrix. It follows that this matrix H is a PCM for C24. Recall also that C24 is a self-dual code, and so G is also a PCM for C24, and H is also a GM for C24. Our goal in this lecture is to develop an efficient decoding algorithm for C24. We could use syndrome decoding for C24 because the syndrome table wouldn't be that large. C24 has 2 to the 12, which is 4096 code words, and so the syndrome table for C24 would be small enough for most software applications. However, the storage could be too expensive for some hardware implementations. And so the goal of our decoding algorithm is to use as little storage as possible and to be suitable for hardware implementations. Since C24 has error correcting capability 3, the objective of the decoding algorithm is to always make the correct decision if the error vector has weight 0, 1, 2, or 3. If the error vector has weight greater than 3, then we don't care what the decoding algorithm does. So when we develop the algorithm, we'll make the assumption that the error vector has weight at most 3. Now recall that the error vector has the same syndrome as the received word. So the decoding algorithm first computes a syndrome S of the received word R, and then looks for a vector E of weight at most 3 that has the syndrome S. If such a vector exists, then the decoding algorithm will decode R to R minus E. And this will be the correct decision, assuming that the error vector has weight at most 3. And this is because the coset containing R contains at most one vector of weight at most 3. And so, if we have found one such vector E in the coset containing R, then E must be the error vector. If no such E exists, then the decoding algorithm will reject R. So as I just explained, if the error vector has weight at most 3, then the decoder will always make the correct decision. If the error vector has weight greater than 3, then the decoder might reject R, which is the correct decision, or it might decode R to a code word different from the transmitted one, and that would be an incorrect decision. Let's develop the decoding algorithm for C24. I'll write the received vector R in 2 halves x and y, and the unknown error vector E in 2 halves E1 and E2. So x, y, E1, and E2 are binary vectors of length 12. The decoding algorithm computes a syndrome of the received vector R, and then looks for an error vector of weight at most 3 with the same syndrome. This search looks for 5 types of error vectors, in the order A to E. Type A is the case where the error vector is the 0 vector, so both E1 and E2 have weight 0. Type B is the case where the right half of the error vector is a 0 vector, and the left half has weight 1, 2, or 3. Type C is the case where the right half of the error vector has weight 1, and the left half has weight 1 or 2. Type D is symmetric to type B, and type E is symmetric to type C. You can check that these 5 cases cover all kinds of error vectors of weight at most 3, and that these 5 cases are not mutually exclusive. In step 1, we look to see if the error vector is of type A, namely the 0 vector. So we compute the syndrome S1 of R with respect to this PCM, and we check whether S1 is 0. If it is, then we accept R and stop. This is a correct decision, provided that the error vector is the 0 vector, because the 0 vector has syndrome 0, and it's the only vector of weight at most 3 with syndrome 0. So step 1 correctly handles the case where the error vector is the 0 vector. Step 2 handles the case where the error vector is of type B. So the right half of E is 0, and the left half has weight 1, 2, or 3. The syndrome S1 of R is also equal to the syndrome of the unknown error vector E. And this can be written as E1 transpose plus B times E2 transpose. Now, when we are in the case B, E2 is 0, and so B E2 transpose is 0. So S1 is just equal to E1 transpose. So if the error vector is of type B, then its syndrome is E1 transpose, which has weight 1, 2, or 3. And thus, if S1 has weight at most 3, then we'll correct X in the positions corresponding to the 1s in S1 and stop. In other words, in this case, we're taking the error vector to be S1 transpose with 12 0 bits appended to its right. If the weight of S1 is at most 3, then the weight of E is also at most 3. And this error vector has syndrome S1. That's the same syndrome as the received vector. And so if the error vector is of type B, then we will make the correct decision in step 2. Step 3 of the decoding algorithm will handle the case where the error vector is of type C. So the weight of the right half of the error vector is 1, and the weight of the left half of the error vector is 1 or 2. Recall that the syndrome S1 is E1 transpose plus B E2 transpose. If we are in case C, then B times E2 transpose is a single column of B, or a single row of B since B is symmetric. So S1 is equal to a single column of B with 1 or 2 bits flipped, depending on whether E1 has weight 1 or weight 2. And so in step 3, we proceed as follows. We compare S1 with the columns or the rows of B. If any column of B, say the ith column, differs in exactly one position, let's say the jth position, from S1, then we decode R by correcting X in position J and correcting Y in position I. In other words, we select the error vector to be uj, ui, where ui and uj are the ith and jth unit vectors of length 12. This error vector has weight 2, and you can check that its syndrome is equal to S1. The other subcase is where S1 differs from the ith column of B in exactly two positions, let's say the jth position and the kth position. In this case, we correct x in positions j and k, and we correct y in position I. In other words, we're selecting the error vector to be uj plus uk, comma ui, where again ui, uj, and uk are unit vectors of length 12. Again, you can check that this error vector e has weight 3, and its syndrome is equal to S1. So in both subcases, we've selected an error vector of type C, so the error vector has weight at most 3, and its syndrome is S1, which is the same as the syndrome of the received word. So in step 3, if the error vector is of type C, then we will make the correct decision. Step 4 of the decoding algorithm deals with the case when the error vector is of type D. This case is symmetric to the case B. So here the left half of the error vector has weight 0, and the right half has weight 1, 2, or 3. So step 4 will be analogous to step 2. However, instead of using S1, it uses S2, which is a syndrome of R with respect to the other PCM for C24. So now S2 is also the syndrome of the unknown error vector, BE1 transpose plus E2 transpose, which now is E2 transpose. If the weight of S2 is at most 3, then we correct Y in the positions corresponding to the ones in S2, and we stop. So in this case, we're taking the error vector to be 0 in its left half and S2 transpose in its right half. You can check that the syndrome of this vector E equals S2, and so E has the same syndrome as the received word R. This means that we will make the correct decision in step 4, provided that the error vector is of type D. Step 5 handles error vectors of type E. This step is analogous to step 3, but it uses the syndrome S2 instead of the syndrome S1. If the algorithm hasn't terminated in steps 1, 2, 3, 4, or 5, this means that the error vector has weight greater than 3. And so we reject the received word R and stop. I've written on this slide the decoding algorithm for C24 without the justification. R is a received word, and in steps 1, 2, 3, 4, and 5, we check whether the error vector is of type A, B, C, D, or E. In step 6, we reject R. Note that the decoding algorithm requires no storage. Also, the operations involved are very simple, mostly adding rows of the PCMs for C24 and comparing syndromes with rows of the matrix B. Hence, this algorithm is especially well suited for hardware implementation. Here's an example of decoding C24. Let's decode this 24-bit vector R, whose halves I'm calling X and Y. So we compute the syndrome S1 by multiplying this PCM and R transpose. When you compute this product, the left half of R, which is X, is multiplied by the identity matrix, while the right half of R, which is Y, is multiplied by B. And so S1 is X plus BY transpose. When we compute B times Y transpose, where this is the vector Y, then these bits of Y that are 1 pick out the corresponding columns or rows of B. Recall that B is symmetric. So B times Y transpose is the first plus 4th plus 8th plus 9th plus 10th plus 12th rows of B. I've written the matrix B on slide 99 for easy reference. We get the syndrome S1. Since S1 has weight 2, we set the error vector to be S1 transpose appended with 12 zeros, and decode R to R minus E. This is done by flipping X in the second and fifth positions. You can check that H times C transpose is 0, so C is indeed a code word in C24. Here's a second example of decoding. Let's decode this 24-bit received vector R. So we now compute the syndrome S1, which is this vector. S1 has weight greater than 3. So now we compare S1 with the rows of B. And we see that S1 differs in positions 6 and 7 from the fourth row of B. So we set the error vector to be this vector, where the left half has 1s in positions 6 and 7, and the right half has a 1 in position 4. We decode R to R minus E to get this code word. Again, you can check that H times C transpose is 0, and hence C is indeed in C24. We've seen that the C24 decoding algorithm only needs to store the matrix B, which is only 144 bits in size. In contrast, a syndrome table for C24 has size approximately 98,000 bits. Also, decoding is very efficient and simple. By simple, I mean the operations are just adding rows of B together to compute syndromes, and comparing a syndrome with the rows of B. And so, the C24 decoding algorithm is very well suited for hardware implementation. I'll mention that C24 was used in the Voyager space mission to transmit photographs of Jupiter and Saturn back to Earth.
In V4c, which is a short lecture, we'll justify why the binary Golay code, C24, provides more reliability than comparable Hamming codes and binary replication codes. Alright. So have a great day.